Hello, I am Dr. Rashmi Deshpande and this is my channel RD Physics. This is the course on atomic and molecular physics and it is third lecture of the series. So today we are going to discuss about the Schrodinger's time independent equation for hydrogen atom by method of separation of variables. So we are going to separate the Schrodinger's time independent equation for hydrogen atom into three differential equations so that it is easy for us to solve these differential equations. If you remember, in the previous session we have discussed what is spherical polar coordinate system and how it is related to the Cartesian coordinate system. So at the end of the last lecture we have seen what is Schrodinger's time independent equation in three dimensions. So equation number 1 is Schrodinger's time independent equation in three dimensions. Del square psi plus 2m upon h cross square into E minus V psi equal to 0. Let us see what is the significance of each term. Del square psi, del square operator in spherical polar coordinates we have seen in the previous lecture. Psi is the wave function of the particle for which the equation is written. M is mass of the particle. Capital E is total energy of the particle and V is the potential experienced by the particle. So this is the equation number 1 is the Schrodinger's time independent equation of a particle in general, and if we want to write Schrodinger's time independent equation, in short we will call it as STIE. So STIE for hydrogen atom we are going to write by using the potential V of R, V function of R is equal to minus E square divided by 4 pi epsilon 0 R. This is the electrostatic potential energy of the electron in hydrogen atom, because we know that the electron revolves around a positively charged nucleus under the Coulomb force. So the potential energy of the electron revolving around the nucleus in hydrogen atom, it is a function of radial distance from the nucleus. So it is a function of R. Small e is charge on the electron and R is the radial distance of the electron from the nucleus. Epsilon 0 is permittivity of free space. So if we substitute this particular expression for the potential in equation number 1 and by using the del square operator in spherical polar coordinate system, then by multiplying throughout by r square sine square theta, the equation that we get is this equation. Okay, so 1 upon r square del by del r square del by del r plus 1 upon r square sine theta del by del theta sine theta del psi by del theta plus 1 upon r square sine square theta del square psi by del phi square plus 2m upon h cross square into E plus E square upon 4 pi epsilon 0 r into psi is equal to 0. So here we have just substituted the del square operator. This is the del square operator operating on the wave function psi. Okay, So del square operator operating on the wave function psi of hydrogen atom, or more precisely, wave function psi is the wave function of electron in the hydrogen atom. Then we have substituted the expression for V, because it is a negative potential, minus minus will become positive, so we get this particular term, okay, is equal to 0. Then if we multiply the whole equation with r square sine square theta, we get this. See, here please remember that how we are going to proceed. We want to simplify this particular second order differential equation. Now it is containing all the three variables, that is r, theta and phi. Okay, we want to simplify this particular differential equation, and we want it to be converted into three differential equations, each containing only one variable, r, theta and phi. Okay, so we want to get rid of one by one all the variables. Means we will try to simplify the equation in such a fashion that the equation will contain only one variable at a time. So if we look at this particular equation, see, the first term contains only r, but the second term has r and theta, the third term has r, theta as well as phi, and the last term contains again only r. Okay, so actually the procedure should be such that, see here, the phi term, if you look at the differential containing phi, then it is just del square psi by del phi square, whereas otherwise you will see that the partial derivatives are containing partial derivatives with respect to r, as well as there is this r square. So this del by del r will be operating on this particular term. Similarly, this del by del theta will be operating on this multiplication, whereas here there is just del square psi by del phi square. So if we can get rid of this term containing r and theta, okay, then there will be just partial derivative with respect to phi. So that is why we are first multiplying with r square sine square theta, and remember that we have to multiply the complete equation, both sides of the equation, LHS as well as RHS, so that the value of the equation does not change. Means the equation will remain unchanged if we multiply both the sides with the same multiplication factor. Okay, so therefore we have multiplied both sides, that is LHS and RHS. On the RHS we have just 0. So multiply the complete equation with r square sine square theta. So we if we carry out this multiplication, we can see that this r square will get cancelled. There will be just sine square theta, then this del by del r as it is, this bracketed term as it is, and here this r square will get cancelled. Already there is 1 upon sine theta, so here there is a sine square theta, so we have just sine theta multiplied by this term, plus r square sine square theta is there. Okay, so we can see that this r square sine square theta gets cancelled, just del square psi by del phi square is there, and this particular term is written here, okay, by multiplying with r square sine square theta. Okay, why we have written this del square psi by del phi square at the end? It is just because this is the term which is containing only phi, whereas all the other terms, they contain both the variables r square, both the variables, that is r and theta. Okay, this is the only term which contains phi only. Okay, does not contain r and theta. Okay, so let us move to the next slide. Now let psi is a function of because it is a function of r theta phi, let us consider that it can be written as a product of three functions, capital R, capital theta and capital phi, where each of these functions depend upon only one variable. Okay, so we are writing psi r theta phi as a product of these three functions, r which is a function of only small r, theta which is a function of only theta, and phi which is a function of only phi. This is called as separation of variables. Okay, and generally whenever there are such more number of variables are involved, this is the method which is followed to simplify the differential equation. Okay, so by using the rules for partial derivatives, del psi by del r will be equal to theta phi del r by del r. Why? Because we know that if the function contains theta and phi and we are calculating the partial derivative with respect to r, so the terms containing theta and phi will be treated as constant. Okay, so similarly we can say del psi by del theta will be r into phi into del theta by del theta. Please remember that capital letters denote the functions whereas small letters denote the variables. Okay, so whenever you are writing, please be careful that you use proper notations. So del psi by del phi is r into theta into del phi by del phi. So therefore the double derivative, okay, del square psi by del phi square is r theta del square phi by del phi square. Okay, so this is by the rules of partial derivatives. So if we substitute psi r theta phi as a product of three functions, then what do we get? We are substituting this in our previous equation, that was equation number 3, which we had obtained by multiplying the Schrodinger's equation with r square sine square theta. Okay, so if we substitute for psi in this equation, then what do we obtain? Just have a look. I have substituted in place of psi, I have substituted r theta phi. In place of psi, here also just r theta phi. So wherever there is psi, I have just substituted r into theta into phi. Okay. Now, as shown in the previous slide, we have to apply the rule of partial derivatives, and so partial derivative with respect to r will give me this theta phi as treated as constant, so they are outside the derivative sign or outside the derivative operator, and we have here sine square theta, theta phi, del by del r, r square del r by del r. Okay, similarly here when the partial derivative with respect to theta is operating on this r theta phi, r into phi will be taken out of the partial derivative operator. Okay, so we get this particular expression. Then now you can see that if you observe each of the terms, then this contains theta phi, this contains r phi, this also contains again r theta. Okay, and this has r theta phi. Now see, this particular term, it is containing phi as well as r and theta. I do not want this r and theta to be there, so that this should contain only phi. Okay, so what I will do, I will just divide throughout by r into theta into phi. Okay, so what will happen, I can get rid of this theta phi from the first term. Okay, in the denominator there will be then only r remaining over here. Similarly in the second term, this r into phi will get cancelled. Okay, only theta will remain here. and here just phi will remain in the denominator, r and theta will get cancelled. Here r theta phi, this r theta phi will get cancelled. Okay, so just have a look. We are removing the unwanted terms by dividing throughout by r theta phi. So the first term contains capital R in the denominator, the second term contains capital theta in the denominator, third term has capital phi in the denominator, it has only phi. The term contains only phi variable. It is dependent only upon one variable. Okay, and here no r or theta or phi is means the function r theta phi are not there. Okay, so we have reduced this equation such that we get at least one term which contains just one variable. Okay, fine. So have a look at this particular expression. What we have done, just we have shifted the term containing phi on one side. Why? The reason is, if you look at this term, it contains only one variable phi, whereas the terms on the LHS contain terms in variable r as well as in theta. And we are saying that LHS is equal to RHS. Please remember, LHS is equal to RHS, but RHS contains only phi, whereas LHS has terms containing r as well as theta. This can happen only if both the terms are separately equal to a constant. Let this constant is denoted by ml square. Okay, let this constant is denoted by ml square. So therefore we can write this particular equation separately. LHS is equal to ml square and RHS is equal to ml square. So if this is equal to ml square, we can write that d2 phi by d phi square plus ml square phi is equal to 0. We have replaced partial derivative with total derivative because it contains only one variable. So therefore we can replace partial derivative with total derivative. Okay, so by equating RHS to ml square, we get this particular differential equation. So equation number 7 and 8 are obtained by equating LHS equal to ml square and RHS is equal to ml square. What is this ml square? That we will see afterwards. Okay. Now dividing equation 7 with sine square theta and then separating terms with r on LHS and terms with theta on RHS. See what we are doing. We do not want the term containing theta in first term, that is which was containing partial derivative with respect to r. Similarly, we do not want terms containing r in the derivative terms containing theta, means derivative with respect to theta. So what we are doing, we are dividing the equation with sine square theta. Okay, so what does it give me? 1 upon r d by dr, r square dr by dr plus 1 upon theta sine theta. Okay, because already there was this sine square theta in the denominator, so that is cancelled. Okay, and we have this 1 upon theta sine theta d by d theta sine theta d theta by d theta. Okay, there was one sine square theta in this term also, that has got cancelled, and because on the RHS there was ml square, and so in the denominator there is this sine square theta. Okay. If you look at this particular expression, the first term has only r, this term also has only r, these two terms contain theta, only theta. Okay, so we will take these terms containing only r together, the terms containing only theta together. So again with the same argument that LHS has only terms containing r, RHS has terms only containing theta, and because LHS is equal to RHS, this can happen only if both of them are separately equal to a constant. Let us denote this constant by L into L plus 1. Why we are taking this constant as L into L plus 1? What is this L? That also we will see afterwards. So rewrite LHS is equal to L into L plus 1, RHS is equal to L into L plus 1. Okay, so this equation number 10 splits up into two equations, 1 upon r d by dr of r square dr by dr plus 2m r square upon h cross square e plus e square upon 4 pi epsilon 0 r is equal to L into L plus 1. This is equation number 11. And ml square upon sine square theta minus 1 upon theta sine theta d by d theta of sine theta d theta by d theta is equal to L into L plus 1. This is equation number 12. Okay, now shift L into L plus 1 on LHS and divide throughout by r square. Why? Because we want that these all terms should be on the left hand side and right hand side should be equal to 0. Okay, so if we do this, then 1 upon r square into 1 by capital R d by dr of r square dr by dr plus 2m upon h cross square e plus e square upon 4 pi epsilon 0 r minus L into L plus 1 upon r square is equal to 0. Just multiply this particular equation by capital R. Okay, so we get this equation number 13. You can see we have just multiplied throughout by capital R. Okay, also shifting terms on LHS of equation number 12. Okay, we are shifting terms on LHS to RHS. Okay, so that we get this minus sign will become plus sign and 1 upon sine theta d by d theta sine theta d theta by d theta plus this L into L plus 1 minus ml square upon sine square theta and multiplied by theta. So here we have multiplied by capital R, here we are multiplying by capital theta. So that is equation number 14. So you can see here that equation number 13 contains only variable r, equation number 14 contains only variable theta. So thus we have separated the Schrodinger's time independent equation which was containing 3 variables. We have separated it into 3 differential equations. So this is our equation. We have rewritten it here. This is theta equation rewritten and this is phi equation. Okay, so afterwards we will solve and we will see that each of these equations gives us a quantum number which is important for the knowledge of the energy values of the electron in hydrogen atom. Okay, so out of these 3 equations you can see that equation number 8, which is phi equation, that seems to be more simple equation. So actually we will solve this particular differential equation and obtain what are the possible values of ml, that is the magnetic quantum number, The solutions of r equation and theta equation we are not going to obtain, but we will discuss the solutions of all these three equations and try to get more and more information about the different properties, different physical properties of the hydrogen atom. Okay, so today we have seen how the Schrodinger's time independent equation for hydrogen atom in spherical polar coordinate system can be reduced to three simple differential equations, and what information we can get from these differential equations, that we will see in the next lecture. So thank you very much for watching patiently.